Okay, and so before we start topic two, just show you these ahead of time. You can pause the video if you want, take a look at them. Okay, we're going to look now at the kind of the layers of the earth. What is it made of? So these are the big ideas you should be looking out for as you go, or that you should come away with at the end. Okay, so now that we've kind of talked about the when of the earth, the how old earth is, right? Our next step in getting to know the earth is, well, what's in there, right? What is the earth actually kind of made out of? And how's it put together? How old are you, Earth? What's your history? Okay, now what are you made of, Earth? So let's take a look. So before I start talking about the structure of the Earth, I'll just take a quick moment to say how we know some of this, okay, or at least how we are able to make some predictions about the makeup of the Earth. So essentially, how it works, okay, is that the seismic waves, which come from earthquakes, basically show us that the Earth has layers, okay, with different properties. Why do they do this? Well, the Earth has layers, okay, like an onion. Why do the earthquake waves tell us this? Well, the speed of a wave depends on the material it's moving through, which you actually knew that, right? You might not have ever thought about it, but imagine you're sitting in a tub full of water and you're kind of splashing your hands to make some waves. Those waves are going to travel pretty quick, right? They're going to go bloop, bloop, bloop. They're going to kind of spread out from away from you. Now imagine you're in a bathtub full of maple syrup, different material. It has different properties. It's denser, it's thicker, right? And so when you make the waves in that maple syrup, imagine the waves now. They're going to go away from you a lot slower. They're going to go bloop, 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 right? So waves travel through different materials at different speeds. Some materials don't let waves through at all, okay? And when waves suddenly change speed, their direction also changes. Okay, what that means is when there's an earthquake wave, right? So when a wave from an earthquake travels through the earth, we see that they change direction suddenly or even stop. So they must be traveling through layers with different properties, right? So for example, you can see here they have, what if there was an epicenter of an earthquake here, right? If the earth was all made of the same stuff, we would just see the waves all go through no problem, right? They would just kind of travel through the earth. They would just go around. However, we don't see that, okay? We see, for example, here that some waves don't make it past this part at all. And we actually know, okay, certain kinds of waves don't travel through liquids. So this must be a liquid, okay? And then we see, right, and we see some get bent as they enter different layers and they kind of move around. They don't quite go straight through. If the earth was all made the same the whole way through, if it was just a solid ball of just the same stuff, this wouldn't happen. Waves would just go straight through, okay? So we see them bend, we see them suddenly change direction, we even see some get stopped. And we can kind of, from that, piece together, do the math on how waves travel, figure out roughly where one layer ends and another begins, and roughly what that layer is like in terms of its properties. So that's just kind of the how. Okay, so now we've gone how we know their layers. What are the layers? Okay. Now, before we get started on this, there are two main ways that scientists divide and organize the Earth's layers. I just want to get this out of the way because you have probably learned in previous science classes what's called the compositional layers. Okay. So you probably know these from previous science classes as the crust, the mantle, and the core. Okay. So the compositional layers, what does that mean? It means we've got all these layers of the earth, or we've got the earth. How are we going to split it up into layers? Well, one option we could do is sort them based on what they're made of. Then you would be doing the compositional layers, right? Composition means made up of. So that's saying, look at their chemical properties. Is it made of iron and nickel, or is it made more of magnesium, whatever? And then sort it based on that. That's a great way to sort it, sure. Okay. However, that is not what we're going to focus on in Science 20. So again, in previous science classes, you probably heard these three, the crust, the mantle, and the core. We are sort of going to leave those words behind in Science 20. Not leave them behind, I shouldn't say, but we're not going to focus on those three layers, the crust, the mantle, and the core. Instead, we're going to sort them a different way. So we could sort them based on what they're made out of, or we could sort them based on how they behave. What are their physical properties? Okay, so that's stuff like density, temperature, state of matter. What does state of matter mean again? Remember, state of matter means, is it solid, liquid, or gas? Right? So that's another way we could sort them. And that's how we are going to kind of look at them in Science 20. Okay. Now there are 5 physical layers. I didn't write them out here because we're going to write them out on the next part here. So there are 5 physical layers compared to the 3 compositional layers. So it's no longer crust, mantle, and core. Okay. So here is kind of a nice picture showing you the difference between the 2 ways of sorting it, right? So on the right side here, we are going to do these ones. These are the physical properties. So maybe just make the note. We use these layers in science 20. We don't use these layers in science 20, right? So notice over here, they've got it split up into three. They got the crust, the mantle, and the core. Notice how they're splitting it up too, right? They're saying the crust is made of granitic and basaltic rocks, what it's made out of, right? The mantle is made of silicate materials, again, what it's made out of. And then the core is made up of iron with nickel and sulfur, right? That's what it's made out of, okay? How are we going to split it up? We're going to split it up based on how it acts. So these kinds of things are important. The rigidity, so rigid, rigid, plastic, rigid, liquid, right? Solid for the bottom, okay? Or rigid, I guess they use, okay? So these are our five physical layers, and we're going to look at them in detail on the next page. But we have the lithosphere, the asthenosphere, mesosphere, outer core, and inner core. So again, just to drive home the difference between chemical, the compositional chemical layers, and the physical layers, right? We don't care what they're made of. We care about how they behave, right? So for us, in this one, we would kind of treat water and milk as the same thing, right? Because they kind of have the same physical properties for the most part. They're both liquids, right? You can't stand on both of them. They're both about the same density. Whereas if we were splitting them up this way, we would split them up because obviously water and milk are not the same, not made out of the same stuff. Okay, so let's look at these layers and what their properties kind of are now that we're getting to know them. First things first, though, you got to know this, okay? As you move deeper towards the center of the earth, and it does make sense when you think about it, right? As you move deeper towards the center of the earth, density, pressure, and temperature all increase, okay? So it gets hotter, it gets more dense, the pressure gets higher. Okay, so let me just kind of draw that in here really quick. So as we go this way, as we go from the surface into the earth, okay, deeper and deeper, density, temperature, pressure, all increase. So it gets hotter, denser, and there's more pressure, right? That makes sense. If you're down here, think about it. The entire earth is on top of you. It gets more dense. You're going to feel a lot of weight on your shoulders, right? Have you ever dove down to the bottom of the pool, right? What do you start to feel? You start to feel it squeezing in on your head. You know why? That's all the water above you weighing down on your head, right? Water's not heavy. Have you ever held like a big Culligan bottle? Or water's heavy. I mean, water's, it's not light is what I meant to say, right? It's squeezing on you. So if you imagine all the Culligan bottles that are on top of your head when you're at the bottom of the pool, that's the weight of all that water on you. That's why you feel that pressure. Okay. So imagine now you're going this far down under the earth. Your pressure is going to get very, very high. Okay. The temperature, some of it is left over from when the earth first formed because it was very hot. A lot of it, though, actually is just from the decay of radioactive elements that releases energy. Okay. All right. So let's start with our first layer. Now, as for the density, okay, why is that? Why is the more dense stuff down there? Well, let's think about it. I'm going to show you a quick video, just kind of a density tower. Right? So what you just saw in the video, why did they kind of organize themselves into layers? Well, it was all based on density. So the more dense stuff on the bottom and the less dense stuff on the top, right? That's why a boat or a piece of wood floats. It's less dense than the water, but a rock sinks because it's more dense than the water. So when the earth first formed, all this stuff was kind of everywhere throughout the earth, but over the billions of years of history, the denser stuff sank down to the bottom and the less dense stuff kind of stayed on top. And so the earth is essentially just a huge density tower. right? So if I were to take that one in the video that they had there and I were to take it and shake it up and shake it up, that would be kind of what the Earth looked like at first. But I could actually take that density tower, shake it up, and then if I let it sit long enough, guess what would happen? It would reorganize itself because stuff floats based on density. So if I left it overnight, it would end up looking pretty close to how it looked there in the video. And that's what's happened with the Earth over the last 4.5 billion years. So when we say the denser layers are at the kind of the center of the Earth, that's not really like an accident that happened, right? They are at the center of the Earth because they are the most dense. That's how they got there in the first place. Okay, so the first of these, the lithosphere. This is very thin. Okay, now the first of these is the lithosphere. This is a very thin layer. It's only 10 to 200 kilometers thick. Okay, this is the solid region. So it's solid, okay, and it's rigid. It's the outer portion of the Earth. Reach out, touch the ground, jump on it, you're jumping on the lithosphere. Okay, that's where you are, the lithosphere. In fact, that is the only place any human has ever been. We have never come close to getting through even the lithosphere. Okay. Okay, the deepest hole that we've ever dug was about 12 kilometers deep. Okay, that was not where the lithosphere was this thick. The lithosphere is only that thick at places like the deepest parts of the ocean. Okay, so up here on land, we have even less chance of digging through the lithosphere. And so we really we've this very outer portion of our Earth, we really have never even dug into that very far. A way of picturing how big the lithosphere is, I've heard it said before, that if you imagine an apple, so take an apple, cut it in half, okay, the skin of the apple as you see it would now be about the lithosphere. Okay, where you and everything that's ever lived has spent all of its time on Earth, right? Nothing has ever gone below the lithosphere, just the skin on the apple. To really put it in perspective, take a look at this. This is Mount Everest, and then if we zoom back out, we'll see how Mount Everest, right? The biggest mountain on Earth, the highest point on Earth. If we zoom out, look at it, disappears. It's nothing compared to the size of the Earth. And Mount Everest is the tallest point on the whole lithosphere. But when we zoom out and look at it compared to the whole Earth, right, it completely disappears, and you kind of see how thin of a layer the lithosphere actually is. Okay, now the lithosphere kind of floats on top of the next layer, okay, which is the asthenosphere. That's going to become important later, that it floats on it. Okay, now the asthenosphere is kind of weird. It is a solid, okay, so it is solid. Don't make the mistake of calling it a liquid. It's a solid, but it still flows very slowly. And you might be saying, how can a solid flow? Well, you've had experience with solids that flow. Think about, for example, silly putty or Play-Doh, right? Those are solids. They're definitely not liquids, okay? But imagine holding silly putty still for a very, very long time. What does it start to do? It starts to deform, right? And kind of drip and droop. So it's definitely a solid. Same goes for Play-Doh. But over a long enough amount of time, and remember, Earth's plenty old, so these things might happen slow, but it's a long enough time that it can actually make a pretty big difference. Okay, so it flows like silly putty or Play-Doh. What this is going to end up being really important for is the fact that as it flows, it drags pieces of the lithosphere around. That's going to be huge later, super important. Okay, the next layer we have to look at. This is our first. So look at those asthenosphere and lithosphere. Okay, notice this isn't definitely not to scale, because if it was, it should be even tinier, right? But notice that by far those first two layers are the smallest, right? The asthenosphere is kind of this small little layer. Sometimes people call it a layer of lubrication, right? Because it flows. So that's kind of the lubricant between the lithosphere and the mesosphere. So the mesosphere is also solid, okay, but it's rigid. It's not like the asthenosphere. It doesn't flow. Doesn't flow like the asthenosphere. It's more solid, okay? So that is the mesosphere. Remember, what did meso mean when we said Mesozoic? It meant middle. So this is kind of the middle. We're 2 layers down, right? Meso means middle. We're 2 layers down. We've got 2 to go. So we're right smack dab in the middle at the mesosphere, middle sphere. Sphere really does mean sphere too, right? Remember, a sphere is a 3D circle, basically. So the Earth is a sphere made up of these layer spheres, okay? Then we get to our next layer, the outer core. This one's interesting. Remember how we said that some waves can't pass through liquids? Well, that's what let us know that, hey, there's something in the middle of our Earth that is clearly made out of a liquid, because these waves cannot get through it. That was our outer core. So the outer core is the only layer of the Earth that is a liquid. Okay, so it's a liquid alloy, which alloy just means a mixture of metals, basically, okay, of nickel and iron. Nickel and iron are very dense. They're some of the densest elements that occur naturally on Earth in large amounts. And so that's why they're kind of down at the bottom at the core, right? Dense stuff sinks over time. What's interesting about the outer core, what's important about it, is you owe your life to the outer core, right? And so does everything else living on the planet now or in its past, because the spinning of the outer core, since it is a bunch of liquid metal, right? That actually, a moving liquid metal full of electric charges will generate a magnetic field. So the spinning of the core produces Earth's magnetic field. That is really important. The outer core produces our magnetic field. Without our magnetic field, we would actually get roasted pretty quick by the sun. Our atmosphere would get blasted away. Okay. Mars, they think, used to have a pretty good atmosphere. Might not have been a bad place to be, except it was missing a iron liquid core like we have. So it didn't have a magnetic field. And guess what happened? The sun blew its atmosphere away. Fast forward, now you probably know Mars is not a great place to be for a living thing. So thank you, outer core. And good thing you're liquid. Okay, then we have the inner core. Makes sense that comes next. That's the most inner layer, right? The core is on the inside, and then the inner core is definitely on the inside. Okay, the inner core, again, like I said, outer core is the only liquid layer, so the inner core is solid. Okay, it is very rigid. Why is it solid? Well, the outer core was liquid because it was so hot it melted the metal. Okay, but then what happens is as you get deeper, the pressure increases so much that it actually doesn't matter how hot it is, it comes back to being a solid. Okay, the pressure is so high that it just gets squeezed basically into being a solid. Okay, and it gets hot. It's very hot. Temperatures here are as high as the surface of the sun, about 6,000 degrees Celsius. So I use a trick to help me remember the layers because these are not in your data booklet, so you do kind of have to know them in order. But I use the saying, Lisa always mixes Oreo cookies and ice cream, right? For lithosphere, asthenosphere, mesosphere, Oreo cookies is outer core, ice cream is inner core. Realistically, I'm sure you can probably remember inner core, outer core, right? Those are hard to mix up. And so then it's just Lisa always mixes Oreo cookies and ice cream. Okay, so that's topic 2. If you're looking to practice, check the Google Classroom or the agenda for which questions go with that topic. Okay, and bringing these up at the end again, just take a look, go through them, answer them in your head or on paper, whatever, however you want to study this, okay? But always a good way to check in with yourself is, can you do the big ideas?